My name is Marco Ricchetti, and I will chair this event, this session, for grid and demand response papers. So I will present Paula Peña, that will be the first presenter from CIEMAT, and she will present hybrid ICDC architecture in CEDER-CIEMAT microgrid. In particular, this is the demonstration of the TIGON project. So, Paula, you can start your presentation.
Okay, thank you. Good morning for all. My name is Paula Peña-Carro, and I work in the microgrids department at CEDER-CIEMAT. And I will now present one of the European projects we are currently working on. The name of the project is TIGON, the abbreviation of Towards Intelligent DC-based hybrid grids, optimizing the network performance. The main objectives of this project are demonstrate the feasibility of DC architectures applied to microgrids and the possibilities they offer, the advantages and disadvantages of DC microgrids when compared to AC microgrids, development of power electronics equipment, systems and software to carry this out, and lastly, to consolidate all the control systems, topologies and applications. So these solutions can become a commercially viable technological option. 15 companies take part in this project, from development and service and equipment supply companies to communication or showcase representatives. CEDER-CIEMAT is part of the last group, offering our facilities to make the test for this project. CEDER-CIEMAT is a center for the development of renewable energies located in Lluvia, Soria, Spain. It is a public body under the Ministry of Science and Innovation of the Government of Spain. We have the perfect facilities to do scientific and technological demonstrations. It makes CEDER-CIEMAT the ideal environment to install this project DC microgrids, which will be located in our PEPA 2 facilities. This is PEPA 2, where we are installing the equipment that will be part of the microgrid. In the next slides, there will be a more detailed explanation. But as we can see in the image here, the photovoltaic system, wind turbine, the transformation center, and the buildings that we hope more equipment are already built. In this slide, we can observe the hybrid microgrid architecture at CEDER. CEDER's general grid is an AC medium voltage power grid. This arrives at PEPA 2 transformation center and is reduced from 15 kilovolts to 400 volts. The 400 volts grid is the AC grid we can see in blue. It enters the solid-state transformer to transform the AC grid into a 3 kilovolt DC grid. Here starts the DC grid we can see in red. When analyzing the scheme in detail, we observe a DC medium voltage grid with a bank of lead-acid batteries still in it. A DC low voltage grid that has been transformed by a DC-DC converter, to which the rest of the equipment, wind turbine, AC loads, photovoltaic system, LFP batteries, and DC loads are connected. All of these have their respective converters in order to adapt voltage and power to each one. The only exception are the DC loads, as they don't need the converter. Now we'll be analyzing in detail each of the systems already mentioned, starting from the generation system. First, we have a small wind turbine of 3.5 kilowatts. It consists of a wind turbine, a regulator inverter in order for it to work in AC, and a DC converter to work in DC. This DC converter has been developed exclusively for this project by the wind turbine manufacturer. This equipment has been installed in one of the buildings in PEPA 2 and is now operational. The other generation system is a photovoltaic system of 52 panels with a total power of 21.32 kilowatts. They are already installed in another building, the inverter, so they can work it in AC. AC. And a DC converter that is currently under development by the University of Valladolid. Next, the storage system. There are two types of electrochemical storage. A lead-acid battery bank with 120 cells. It is supported by a DC-AC inverter for a DC-AC operation. In addition, there is a DC-DC converter for the medium voltage grid that is being developed by members of this project. Currently, this system works in AC mode. These two last pieces of equipment are installed separately as the chemical and electrical components need to be separated due to security reasons. And the other one storage system can be found in the building next to one we have talked about before. It consists of 2 racks of LFP batteries of 14 modules each. In addition, there is an AC converter, so the equipment currently works in AC. And DC-DC converter that is being developed by the University of Valladolid. Now, let's talk about the grid's main transformer. They are unrelated to the ones connected directly to the generation, storage, and load system. Solid-state transformer. This device will generate the DC medium voltage power grid from the 400 volts AC. This is the microgrid main transformer and is being developed by 2 companies collaborating in the project. The other converter will generate the DC low voltage power grid from DC medium voltage power grid. It will be placed in one of the buildings once the member in charge of its developed finished. Based on the loads on the microgrid, we can find 2 types. AC load of about 9 kilowatts, to which will be added DC load. The DC converter is being developed by a company specifically hired for this purpose. Lastly, the DC loads. There are 3 loads of 4 kilowatts each have been installed. Each of them is directly connected to the DC low voltage power grid. Until now, we have explained all the components of the microgrid, but in order for it to work correctly and be optimized, we have developed a control system that let us visualize and manage all those elements in real time. Why is it essential to have a control system in a microgrid? Okay, to have the system correctly operating as a whole, to detect, prevent, and mitigate possible problems that may arise, and to study and analyze the global operation on the microgrid. In order to do this, it is necessary to install a network of analyzers in each of the units for real-time readings, enable communications between load units, have the possibility of manual or automatic operation via management software. In our case, this is made with Home Assistant, which let us have a data register and a cybersecurity system to reduce cyber attacks as much as possible. This image shows the interface for our management and control system with Home Assistant. This software allows the creation of different labels in which the user can include the information he wants in each one of them, like readings and action to take all the different elements and parameters. In particular, this tab shows general real-time information about each and every system of the microgrid. data referring to the day, time, information on the overall microgrid, such as consumption, generation or discharge to the grid, and similar data on the generation, storage, and consumption systems in a more specific form for each installed system. If we look closely to the other tabs in blue, we can see other tabs exclusively dedicated to manual and automatic control of the system, or to the storage system, where it's possible to see more detailed information. Okay, in this slide, we see the tab dedicated to lead-acid batteries. We can see the temperature, state, power, errors, power values, and even have the possibility to charge or discharge the system in real time with the desired power set point. The software records all these variations and parameter register. Home Assistant gives the option of making a 24 hours graphic like the one in the next slide. The first graphic shows the power generated by the small wind turbine in a whole day, and the second graphic shows the power registered by the lead-acid batteries. These kind of graphics are viable as with only and fast. Visual analysis, we can observe the equipment's performance and detect possible abnormalities. Finally, a summary of how this project is going and where we want to go. CEDER-CIEMAT is one of the project TIGON's demonstration center, and here an AC/DC hybrid microgrid is being installed. Currently, all the equipment and its inverter are installed in AC and are working under the supervision of a management system. The equipment necessary to operate in DC is being developed and are estimated to be finished in the next year. And then the microgrid will be completely installed and the management system will be uploaded with the new equipment. In addition, a severe security system will be installed. Once these tasks are completed, we will start the DC task to register and analyze data in order to study the efficiency of the installation, energy, expenses, benefits, etc. So thank you for your attention, and I hope the next year we can update all this information with all the advantages that give. Thank you.
We can switch in the next presentation. We have here Vlachkov and Daniel Shangov from ESO. Daniel will present the potential 5G solution for TSO grid observability and manageability of massive west penetration environment in the smart 5 grid context. Okay. Okay. You can present now. Thank you. Hello, everybody. Can you hear me?
Yes.
Oh, okay, I should start over because it was muted now and nobody heard, obviously, what I said. So in a nutshell, I'm here on behalf of the electricity system operator. My name is Daniel Shangov, and I'm here with my colleague Krasimir Vlachkov to represent a project called 5 Smart Grid, a demonstration of 5G solution for smart energy grid of the future. And this is one of the projects that electricity system operator Bulgaria is running in partnership under the European Europe 2020 program framework, and it's about demonstrating how 5G solution in the energy vertical can help manage the changing landscape of the transmission grids and transmission systems of electricity in the context of the energy transition with the high penetration of distributed energy generation, new market players such as flexibility providers, flexibility service providers and aggregators and so on. And also the demand management and also the management of distributed renewable energy resources. So how this 5G technology, wireless technology can help better handle the information background needed to manage these systems. So these are the consortium members. It consists of 24 partners, and it's obvious here that half of them are representatives of small and medium enterprises, mainly from the ITC sector. And also we have telecommunication companies, transmission system operation, distribution system operators, and universities. There are two universities that we have as partners here in this project. It's the University of Cyprus and the National and Cappadocian University of Athens. So these are the main figures of the geographical spread of this project. It started in the end of 2021, and it's about to end, hopefully, in the end of 2023, a total of 3 years and 8 million budget, with 7 EU member states participating. So before I jump to the main essence of this project, I need to say just a couple of words about the traditional power system as we used to know it. It's a kind of a waterfall kind of system with a one-directional energy flow, let's say, going from the centralized power generation to the transmission operator, transmission system operator grid, high voltage grid, to medium voltage transformer and corresponding power distribution system operators, and to the end consumers. However, as we know, in the concept of the Green Deal and especially the latest developments in the energy sector, which are quite turbulent, I must say. We all know that this landscape of the traditional grid has now changed dramatically, and this trend is continues to grow. So that's why these are the main factors that stay behind this change of how the legacy power system has changed and is undergoing these changes, of course, underway. First, we have first and foremost, we have a high penetration of distributed generation. Although technologies are improving in terms of manageability and observability of renewable generation, these resources are spread across all levels of the grid. Let's say we have medium voltage, not only high, they are connected not only with the high voltage grid, but also medium voltage and low voltage grid, small distributed renewable energy resources. So this changes the way the information flow and the energy flows are managed, and requires the use of modern solutions, communication solutions that are add value to the power optic communication and to power line carrier communication, which is the traditional means of communication in the grid environment. So these are the main drivers for this change. We have new actors in the market. That's one point that we should focus on. These are the aggregators and the flexible service providers, meaning the virtual power plant operators and so on. We now have developed the development of smart 5G solution that we can possibly deploy in our energy vertical. And with this penetration of distributed generation and demand side management, we have stability issues that we need to face by using adequate informational and telecommunication solutions. So this is how those drivers has changed the traditional power grid into smart power grid. As you can see here, the generation is not only concentrated at high voltage level, it's spread across medium voltage level and low voltage level. And we have also aggregators and new market actors. So it's a multi-directional, rather than waterfall system. And that's why this project was conceived initially. So why we should use 5G instead of fiber optic or PLC communication. We are not tending to replace this sort of communication, I mean wire-bound communication, but we need to add value, as I said, to them to add more flexibility, better, lower, because they have this wireless 5G solution, have lower deployment costs, as you can see, faster implementation, higher flexibility, and as opposed to the 4G long-term evolution LTE, the 5G also provides slicing capabilities, which means that we can virtually dedicate bandwidth at the same time to various tasks related to the energy management. Here, the main concept of this project is to develop a NetApp solution. A NetApp, as you can see, the definition is an extension of network visualization functionality that provides abstraction to the 5G complexity to allow development of data network functionality to a broader group of people. That is a very complex definition, but the NetApp is actually a chain of virtual network functions serving a specific scenario, bit management scenario, let's say, like this. So this is actually what this project is aimed for is to create an open experimentation 5G platform that is where all any stakeholder across any energy vertical, also the information and communication technology integrators and developers, network application or NetApp developers, telecommunications, small, medium, private, and just about anyone who is interested to step into this market, including startups, to develop, upload, test their network apps serving the energy system needs in an open architecture, open smart 5G platform architecture. So there are 4 use cases of this project, which are trying to touch upon different scenarios, high profile scenarios, let's say, in the power grid. The first is the automatic fault detection and self-healing in distribution grid. This is the Italian demo project, which is trying to develop 5G solutions for monitoring and discerning faults that are occurring in the telecommunication system from such faults that are occurring in the power system, which the end result of this is expected to be better, higher security, lower downtime of the network, and so on. The second use case is to improve safety of maintenance workers in high voltage substations. This demo is located in a substation near Barcelona, where a virtual delimited working area is created using the 5G capability and edge computing in order to protect workers and to improve safety. I will just, if there is time enough, I'll go more to this use case. And use case 3 and 4 is the millisecond monitoring and distribution renewable generation resources. This is exactly what I touched upon in the beginning. We have a medium voltage connected wind turbine that we are trying to monitor better for predictive maintenance and also for real-time operation improvement of this distributed generation. And the last project is the wide area monitoring or WAM system for 2 power grids, the Bulgarian and Greece power grids connected via interconnected that we are monitoring using 5G technologies. So this is the structure of the platform that we are developing now under this project. This is the main deliverable, I may say. So the platform, the open 5G experimentation platform consists of, as you can see, 3 layers. The platform itself, which is the consists of the open service repository and the verification and validation framework. So the open service repository is where the stakeholders can upload, modify, verify, test, and validate their NetApps. And they can also download already validated and ready NetApps in order to modify them and, let's say, put them together with their own development, their own NetApps that they are now developing. So they can use these NetApps as building blocks for other NetApps, let's say, like roughly like this. So the OSR is the place that those NetApps will be located, and the verification and validation framework is the other main part of the platform. This is where these NetApps will be validated, tested, and also verified. So the next level is the network function virtualization. So this is, we can show this the management and orchestration framework. That is actually the telco infrastructure and the cloud and edge computing infrastructure. And at the bottom we see the energy infrastructure, where we use hardware in the loop capabilities in order to demonstrate how the four NetApps corresponding to the 4 use cases are operate actually. So the energy infrastructure, there are the measuring devices, which using the Q capabilities or hardware in the loop are able to represent and to mimic in a virtual way part of the system while experimenting with real-time data without compromising the security of the power system. So these are where the 4 use cases are located. I mentioned this. The use case 1, this is the only use case that is using. Actually, no, it's not the only, but it's using it uses public 5G radio access network for monitoring of real-time identification and isolation of faults in the distribution network, which we call self-healing, using an array of intelligent energy electronic devices, which is its metering equipment, which is measuring various parts of network parameters such as voltage, current, and so on, frequency. So this NetApp is will be created and tested and validated on the platform, is supposed to discriminate the source of a grid fault from the source of a telecommunication fault in order not to mix them together. It's the self-healing automation system, and the end result of this is supposed to be, it should be measured against the key performance indicator in the end, but it should minimize the system average interruption index and the customer average interruption index, which is SAIDI and SAIDI and CAIDI. Using the smart 5G platform and then a dedicated NetApp for use case 1. This is the how it looks. On the left, you see the substation where the measurement equipment and the intelligent electronic devices are located, and you have the radio access network through which the platform is being accessed And the second use case, as I mentioned, this is the improved safety of maintenance personnel by automatically delimited working areas at distribution level. We now use for this use case, we use static and yes, let's say movable sensors. Static sensors mean cameras, and ultra wideband sensors are those that workers are wearing on their helmets, for example, on their wrists. And these are using 5G private core and radio access network in order to send any signals in case of violation of the virtually delimited working area. And this actually prevents life, saves life, which is the most important asset, of course, for any company, let alone the image of the company should some accident occurs due to neglected safety measures. So this one is supposed to use ultra reliable, low latency 5G communication and extended mobile broadband data exchange between these monitoring devices, and all this will be managed by artificial intelligence in order to manage security and safety of workers in the best possible way. This is how the network of configuration for use to this case 2 pilot setup look like. On the left side, you can see the movable equipment, measurable equipment, how it is connected to the core 5G network via customer premises equipment. And on the right side, it's just an analogical picture, but with the cameras, how they are connected to the grid. And this is the whole overall layout of the use case 2 regarding safety of works. This is actually the only use case that is using the private 5G network, consisting both of core network, new radio network 5G, and radio access network. It's all these data that are coming from the sensors are gathered via 5G virtual private network, and then they go to the platform where the NetApps are located. This platform is managed by a Neutron software and is linked to the cloud or edge infrastructure, where, as I mentioned, virtual private network. So, in the semi-final use case 3 is millisecond precise distribution generation control. It's a pilot NetApp application that demonstrates how we can monitor more precisely distribution renewable energy resources, or DRER, in a millisecond range, which what does it mean? It means ultra reliable, low latency, and massive machine type communication network. Plus, these are the 2 network slicing capabilities that we use in the 5G. What we seek to achieve is a high visibility of renewable generation, renewable energy sources production, in order to improve the system control and also to reduce curtailment or shutdown, unintended shutdowns of renewable energy sources for balancing for system balancing purposes, for example. But this also will allow this higher security, will enable higher share of renewables to come up to connect to the network. So we also this use case also will leverage on the smart 5 grid platform to actually meet all these demanding requirements of distributed renewable energy resource management, and actually will facilitate accelerate supposedly energy transition, the green transition. This is just one example of how a NetApp architecture looks like, because NetApp, along with verification and validation and the open source repository, is one of the main concepts of this project. Let's say new developments, like it's innovation aspect. So we have the wind farm sensors and the Raspberry Pi 5G enabled sensors that are placed on the wind turbine. These sensors are measuring 2 types of parameters: weather parameters such as wind speed sun radiation, humidity, and so on. And we also have the electrical parameters that are measured by another set of sensors, such as voltage, current, power, and so on, frequency. So these data are sent to a mirroring device, let's say. It's a Raspberry Pi, which these data is sent to the platform, once again using the platform that is still under development. It's the end goal of the project. So there are two virtual network functions. As I mentioned, a NetApp, which is network application, consists of a chain of virtual network functions. So the two virtual network functions in this use case, this for example, is predictive maintenance and real-time energy production monitoring, which will, the end users of these monitoring services, let's say, and predictive maintenance services will be, of course, the wind farm owner who is able to better manage its system in real time. It will be better able to schedule the maintenance program and, of course, reduce the downtime of in this case, the wind turbine, and they also be able to participate in a more efficient way in the market, providing, for example, flexibility services and so on. The operator will also benefit from this. I mean, the transmission system operator and distribution system operator, by being able to achieve higher transparency of observation. Let's say it will be able to see in a better way the distributed renewable generation. Okay, this is the test bed. I don't have time to go into too much detail. This is how it looks in terms of. Okay, yeah, 2 minutes. In this, the fourth use case, which is the most relevant from a transmission system operator point of view, is how we can manage an interconnected systems, power grids, in this case between Greece and Bulgaria, using 400 kV interconnected between the two countries. So in this use case, we are using data coming from devices installed in both substations across borders in the grid and Bulgarian substation. These are called PMUs, or phasor measurement units, that are sending data via 5G infrastructure to a virtual phasor data concentrator, which then feeds the use case specific network application in order to provide this quick, let's say faster and more flexible monitoring capabilities compared to the legacy. You can see the legacy communication of within substations and outside substation of power transmission grid. You'll see here there is a feedback delays, and there are two levels of communication between the PMUs and the phasor data concentrators, or PDC. Now, this is a more elegant solution on the right, when we can see we use a virtual phasor data concentrator, just one level of communication between the substation level, regional level, and central control room level, which is a more reliable solution and provides more speed of communication and more reduces communication the number of communication faults, let's say. This is analogically how this NetApp application looks like. These are the two PMUs of the post substation that are connected to the cloud infrastructure where the use case for NetApp is running, and the both users of these services is the IPTO and ESO, which is corresponding with the Greek and the Bulgarian transmission system operator. This is the layout, and what we have as innovation aspect, in that I'm concluding my presentation sorry. So SMI5Grid, as you see, is supposed to substantially improve the network end-to-end latency and data rate. In addition to providing reliability and availability, warranty, quality of service, and unprecedented flexibility, we are deploying service-based architecture. We are also using the functional split in a radio access network, which means that we are using radio network access network resources to serve our platform and NetApps scenarios. And the project is using multi-access edge computing or MEC servers on top of network slicing that I mentioned about already, what network slicing is supposed to be. And we also have an management and orchestration of extended mobile, broadband, ultra-reliable, low-latency communication, and massive machine-type communication slicing capability in order to serve as many use cases in the energy vertical as possible. This is how the project goes. The green things represent where we are at now. We have, of course, started the project, defined our use cases, and we are now well in advanced development the open experimentation platform, but there is still a long way to go until we get results and are mature for exploitation and dissemination and market maturity, hopefully in the end. Okay, that's it. If you have any questions, or if I use too many words, but I try to explain some concept that it's in the 20 minutes time, it's not enough to
yeah. So thank you very much, Daniel.
Thanks.
If we have questions, so considering we have a bit of delay, if we have questions, people connected in virtual mode can use the chat, and then we can we can do it at the end, or I can directly connect you with Daniel by.
Okay. In the meanwhile, I give the floor to.
Okay. So thank you very much. We can move to the next presentation. Here we have. Sorry, guys. We have Michael Short from Teesside University. Michael will present measuring the gap, a statistical approach for line evaluation and forecasting of human participation in demand response program. Just keep in mind. No. Okay. Okay, welcome.
Yeah, this one? Yes, that one. I'll try not to pull cables out and wreck the place before we start. Okay, thanks very much for the introduction. Marco, good morning to everyone in the room. Good morning to everyone listening online. Okay, so what's this about? A bit of a speculative one. Starting to have a bit of a think about modeling of demand response. So we heard from the previous speaker about some of the challenges that we face during the energy transition. When we think about stability of an electricity grid, which has large penetration of renewable energies, the balancing of the system, problems to do with forecasting, the need for reliable forecasts for secure economic dispatch. And we're very much interested at Teesside in similar kinds of research problems. But at Teesside, we've also been looking at demand response and different forms of demand response, playing around with the load as well as the supply. We can have fully automated demand response and semi-automated demand response. And semi-automated demand response implies that we have people, human factors in the loop. So we need to start to think about how we can measure some of the performance differences that seem to exist between the assumptions that we make about how people will behave and what we actually observe in practice. And we've seen this in some of our own demonstrations, previous projects, Horizon projects, ideas, Dr. Bob, and our current project, which is the REACT project. Okay, so moving on. So very quick assumption is that pretty much everyone will know what demand response is, but just in case We don't. A very brief overview. So we have an electricity production, distribution, and consumption system. Large penetration of renewables. We have a load, a demand placed on the system. Yeah, get rid of the message. Which produces a daily load curve, which we can predict with reasonable accuracy in a large power system. Now, the availability from renewables obviously isn't going to match what we want in terms of demand. So we can use storage vectors, we can use dispatch controls, and we can also use demand response, which is to try and send commands from the system operator or an aggregator, a distribution network operator, which will influence the load to shift the demand. The idea being that if we can better match this towards the availability of renewables and avoid large stresses on the grid, we can avoid the use of expensive peaking units, economically expensive and also expensive in terms of carbon emissions. So that's the overall concept. And what we would like to think about is demand response in different contexts. Demand response in a residential context, sending messages out through an advanced metering infrastructure. Again, heard the previous speaker, loads of options now in terms of ICT and communications, 5G networks. We can send messages to smartphones, send emails, SMS messages, send messages direct into smart meters and use a bit of local automation. But if we do this on a residential basis, the user has to have some form of control. We can't just start switching on and off an EV charger or a dishwasher. There has to be some constraints, and there's a person in the loop, so human factors have to be considered. Now, in the context of the REACT project, our current project, Horizon 2020, running from January 2019 to December 2023. Part of the call, decarbonizing energy systems of geographical islands. Multiple partners, 23 partners from across industry, energy, universities, RTOs, research institutes, £10 million budget. Key demonstration sites, including the island of La Graciosa in Spain, island of Calaforte off the coast of Italy, and also the Isle of Arran. Almost got that wrong. So what REACT is all about is using renewable energies to create smart community-based energy management systems, which we would hope can make a geographical island independent in terms of its energy use. But we can't have independence on its own, because full independence means a lack of resilience. So the energy transition really is about creating a system of subsystems where each local subsystem has good autonomy in its own right, but is aware that it's an actor in a larger system. So that's the way that we would build up resilience. So thinking about the geographical context, demand response in the context of an island in the Atlantic Ocean, La Graciosa. What are the human factors involved in demand response in that context? Versus, let's say, a community microgrid in Nigeria versus a farming community in the Aran Islands. What are the human factors involved? How do we model them? And how can we forecast them in such a way that an aggregator, a system operator, can make useful predictions about what's going to happen when we send messages out on a demand response system? Okay, so some of these issues start to be considered by my colleagues in the Dr. Bob project, demand response in blocks of buildings. And what they found is that there is a gap. A gap can be well defined in what the viewpoints that the designers, the engineers, and the technical staff, our expectations of how demand response is going to operate versus the way it actually operates in terms of the users. So Now that we've identified that gap, how can we perhaps measure it, do some online measurements and do something about this, turn our demand response from a system that we hope would work with the best of intentions, but maybe falls short, to a system whereby we hope it works with the best of intentions, but when we actually get real data in about the way it is working, we can perhaps adapt and change the assumptions that we have and try and stimulate and make the demand response system work more effectively than if we just do this blindly. So a number of recommendations, a lot of these are offline recommendations, raising awareness, understanding that different demographics have different value propositions and different drivers. But from an engineering point of view, we still want to operate systems which are effective, resilient, cost-effective in terms of the price of energy for the consumer, the profits that can be made and used to sustain the companies and agents that are delivering them, but also one that can achieve climate change goals. So how do we do this? We've kind of got a bit of a blockage, as it were, in the system. But if we abstract, perhaps, and look at demand response in an aggregated system. So looking at, for example, residential households, we did this in ideas in Finland. What makes sense in terms of trying to forecast and understand what's going on in terms of the human factors there? Well, it would be some kind of local model which is regressed or makes use of data that's available locally and builds that into pre-existing knowledge about, for example, interviews with the residents themselves, and incorporates information in a centralized node. Then looking at this from the next level up, an aggregator, a distribution network operator, is dealing with lots of different nodes, each of which has a different context, is able to make predictions, and we want to aggregate those together. And we want the distribution network operator to also be able to make a useful prediction about what might happen if demand response is triggered at a certain point in time. And going even further, we want the high-level system operator, the transmission system operator, to have the global picture and to be able to pick up and all of these small adaptive models, integrate this into the large-scale picture. So the transmission system operator can have reliable forecasts and useful information built into an economic dispatch. Kind of thing, the kind of economic dispatch and demand response that forms, for example, STOR events in the UK, short-term operating reserve. So the design logic, building on previous work of colleagues, the design logic that we use to build into the concepts around economic dispatch should contain an understanding of the user logic, which represents the values, preferences, intentions, and practices of the expected users of a given technology in its specific context. So we're moving into trying to extract very regional, localized information and build this up in a hierarchical layer to produce forecasts. So if we want to measure the gap and try and close the loop, apply feedback, then this implies that we should measure the responses against our original assumptions and refine the design accordingly. And the realized design at runtime, the logic must therefore forecast responses within certain confidence intervals. It's the same as with, for example, forecasting of wind energy availability. It's not going to be 100%. So what kind of statistics do we need to start to consider? We can consider behavioral models based on Markov chains, linear and nonlinear, standard discrete Markov chains, and Markov chains built on, for example, artificial neural networks, stochastic neural networks. So very complicated. I think this is ultimately the way to go, the application of advanced AI. But from the point of view of kind of a starting point, wanted to simplify this down. Steady state of a Markov chain is a multinomial choice. So if we represent the context of a specific user in a specific situation with a specific technology, we can start to create states, logical states, which represent the user in some kind of relationship with the technology. So one state could be the user is out of the house. Another state could be the user is in the house and the appliance is off. The user is in the house, the appliance is on. If there are 10 appliances and 4 users in the house, then you start to get the Markov chain, which is very, very complicated. And the Markov chain is well defined, but we move around states in the chain stochastically. So it's involving statistics and probability. But in steady state, for a number of smart appliances, if we are looking at appliance curtailment in response to demand response events, then we can start to think about picking this up as binomial distribution. And abstracting even further, we know that this kind of problem abstracts into a number of different domains. It abstracts into critical systems, avionics systems, and automotive systems. It extracts into certain types of control, batch process control. And it also abstracts into bioinformatics as well. So some previous work on statistics, a number of papers that are published in this area, trying to pick up something useful that we could actually trial in the context of demand response. Some new equations and representations which simplify the process of estimating with guarantees on probabilistic concentration, things like a binomial proportion. And also very simple but easy to apply guarantees on the concentrations associated with quantiles of a binomial. So apply this over a small or large population. The larger the population, the more accurate the forecasts of the quantiles will become. But the important thing is here, these are inequalities, concentration inequalities. So even as we reduce the population, say 4 or 5 appliances in a household, then we lose a bit of accuracy, but it's still a statistical guarantee. So if we are trying to put a minimum bound with 95% confidence, number of appliances that would be switched off at a certain point in time, when we've gathered some empirical data, we know that it will actually be minimal, a lower bound with a given statistical confidence. And this is simple enough to be built into mixed integer linear programs and linear programs, and also quadratic programs, which are the kind of optimization tools that we use for economic dispatch. So response variables, we can model as certain types of constraints within our optimization problems. And from measurements, from smart meters or user self-reported data, measurements from aggregations of electrical demand, we can start to pick up signature traces and produce confidence estimates of key variables with certain confidence. So again, a lot of simplifications involved here, but I mentioned abstraction. At this point in time, I've started to analyze data from demand response situations, but not enough data to really report in a useful context at this point. Hopefully a follow-up paper, I'll have more data and more analysis. But I mentioned abstraction and what kind of synergies do we have in other domains. And one is bioinformatics. And a problem that we faced during the COVID-19 pandemic was trying to understand the transmission dynamics of the disease itself. And not only the transmission dynamics, but also things like the probability that somebody who was contagious with COVID-19 would require a hospital bed. And again, we're looking at statistics at different levels. For example, in the UK, the national statistics, that's the national picture. We also have regional statistics, the Northeast, the Midlands, the Southeast, the Southwest. And we can break that down to individual points of medical care, individual hospitals. So one thing that I've done is apply a huge amount of data is now available on this COVID-19 outbreak. And in the UK, I've applied these methods to estimate the infection mortality rate across the entire UK population, upper bounds, lower bounds, and average. So that's extraction of signatures from available data, very, very accurate estimations. And also use this to produce a forecast. I'm almost done. To produce a forecast of how many people would be hospitalized in intensive care based on the measurements of data and able to forecast within two limits, red limit and green limit. That's a 95% confidence band. Black trace is the actual empirical data, the amount of people that were hospitalized. So this is at a national level. It also breaks down similar results at regional level. And this is the kind of thing I think that we need to start applying in terms of demand response. Making forecasts between certain limits, upper and lower confidence limit. Okay, this is the response that we might see 4 o'clock on Thursday in this particular area, and then aggregate these forecasts together to a national forecast. Okay, if we trigger a short-term operating reserve at 4 o'clock on Thursday, then we can expect to see a response within these bounds at a certain confidence probability. So that's the hypothesis that I'm hoping to test using data from the REACT project as it comes in from the demonstration sites. Hopefully write a paper up and put it on the Commission portal, which gives an indication of how successful or not the application is on DR data. Okay, so thank you very much. Pleasure to speak at Sustainable Places.
So thank you very much.
Yes.
How do you connect economic dispatch with free energy market?
Oh, that's a wider question.
Okay.
Yeah, economic with an energy market. Yeah, well, the energy market, if we use the example of Alexon in the UK, the economic dispatch, it involves the reported costs from different operators, yeah, and optimizes down to the minimum. Okay.
I have a very quick question. And so REACT is based on islands. And
yes.
Such analysis, statistical analysis you were showing, refer to what one would expect in, let's say, how to say, normal countries, not islands, or this could be one-to-one, let's say, applied also to entire countries such as Germany, which is not an island.
I think the overall message is what we would find on an island, on one island, is different to what we would find on another island, and would be complete difference to looking at a residential community in, say, Finland versus block of flats in central London. So I think we need the message, I think, coming from colleagues in social sciences. We need to be asking questions and making initial assumptions, looking at the specific context. And the message coming from myself, as kind of a mathematician involved in informatics, data science, is that we also need to build a system that's adaptive and can quickly and efficiently extract more meaningful information from the data and close the gap that social scientists have found in demand response. So let's see where we go with it. A much bigger picture. Yeah. A colleague from Teesside now will start to talk about some of our assumptions.
Yeah, I'm really happy that we're in the same session because our contributions integrate in some way and speak to each other. So.
So thank you very much. We will move now to another presentation from Teesside. Here we have.
Questo non ti serve adesso?
No. We have Dana Abi Ghanem. Thank you for the right pronounce. And Dana will present configuring the end user in the design and testing of demand response, implication for user engagement with smart grid solution.
Building scale. We are talking about when we are looking to this.
No, perché l'ha mandato.
So
I think that we have another. Here we have connected with the Regis account. Okay. Okay. I have to switch to this. Okay.
I need to go back to this slide.
Okay.
I need to go back to this slide. Sorry, as I said, I need to go back to the start, so just give me a second. Okay, so I will only just say, because Michael thankfully has introduced the React project, my paper today is configuring the user in the design and testing of demand response. And what we mean by configuring the user is basically how the designers who are involved in the design and implementation of demand response are thinking about the user and how are they designing and scripting their thinking into the actual demand response that will be implemented. This work has been recently conducted by myself, my colleague Mina Najafi, and one of the PIs on the project, Professor Tracey Crosbie, who is not with us here, but she is online. And of course, Michael is also part of this project. So thank you, Michael, for already introducing React. I will skip those slides and delve straight into what it is that we did. Our aim was to understand the expectations of the engineers and designers involved in the React project when they are thinking about demand response and the smart grid and how the demand response will function in the future of the smart grid. And to explore the expected modes of use that the designers are imagining their prospective users will undertake, and how these compare with the actual user geography. In other words, we already had conducted a survey and started doing interviews with the prospective users. And we were interested in how these kind of compare in order to identify the gap that is in React, because as Michael was just saying, context is very important. And each situation, whether it's an island or the blocks of buildings, we need to discover those ephemeral, if you like, things that sometimes slide off each other and don't always necessarily meet and interact in the way we prefer. And finally, a gap in the expectations and designers and users' expectations of VR solutions leads to a gap in expected performance of those solutions. So how do we avoid that? So why study the design process? So this is basically informed by my background. I'm a social scientist. My background is in the sociology of science and technology. This body of work has indicated that designers imagine a user and a user environment and imagine a technological ideal. And the role of the designer is very important here. They play a key role in configuring or shaping the interaction between the user and the technology. So basically how the technology is intended to be used, what for and by whom. There's an element of moralizing, of disciplining that Jelsma talks about. And finally, the gap between the expectations of the designer and what the user wants, a very diverse body of work. And based on that work, our colleagues that Michael has already indicated, our colleagues from the Dr. Bob project alongside Professor Crosbie, that is conducted, we based on that to understand the design logic of the React solution and versus the use logic that will transpire as we carry on our research on the islands, and then identify the potential gap and mismatch between these two logics. We had a qualitative approach consisting of interviews with the designers and the project managers and the innovation managers involved in React. These were the insights from these interviews were thematically analyzed and informed by the sociological perspective that I just highlighted. And so some information about the data. So important to say that the data does not include all my own, because I am part of this project itself. So we did not include any of the discussions that were taking place in the meetings, because these are not covered by the ethical framework that inform the way we approach the work. Instead, our insights are limited from the interviews that we have conducted, which are bounded by confidentiality and anonymity. So the role of users as imagined by the designers. Firstly, it's important to note that almost all the designers, and I will call, for short, I will just call them designers. But of course, they are a diverse group of backgrounds and so they always centered the users. So they perceived the users as the center of the system and as very important to demand response, and that they need to be actively engaged. That they wanted them to be accepting of the recommendations from the grid and to align their consumption to the, for example, their batteries, and live automated lifestyles. So this was mainly the kind of, if you like, the idealized user of the React project, but also very much so in the opinion of the designers, the future of the DR user. However, they worried that the user will be fatigued from over-engaging with constant messages from the suppliers about changing their behavior. So this kind of willingness, this good, the good faith was, there was a constant worry that this good faith will eventually, decrease with time. And so so this is like, if you like, an overview of how the users were constantly thought of. The role of the suppliers in the future of the demand response was seen as like, they are key in that they are the facilitators of change, that they need to invest in demand response, even if they are not doing so as much as they need to, that the supply side also requires aggregators, in particular for residential users who are small in terms of their consumption, that energy companies have to collaborate with other professionals, including social scientists such as ourselves, and that they need to communicate to their customers in a simplified way and educate about the demand response. And also included in our results was this notion that social media and the digitalization of our everyday life needs to also be platformed as part of the smart grid of the future. So, however, it's important to note that our designers also felt that the suppliers are not motivated to change, and because their business model works on short-term benefits, and so long-term investments like demand response and the smart grid doesn't seem to feature as wholly and consistently as they would like, and that strong government policy is always needed to push through those kinds of changes required in the provision and service of electricity. And this is actually something that came out from a previous session I was attending. So the role of the government should not be sidelined here. Finally, in terms of the design and digital interface of demand response again is idealized to be automated, digital-based, streamlined, to have minimal disruption on people's lives, offering different levels of engagement, as Michael was saying, this idea that people engage differently, and so need to be adaptive to that. Open and transparent systems was also kind of indicated as key, as well as perhaps more focused or importantly focused on electric vehicles and transport, because that's where the majority of electricity flexibility can be derived or harvested. And the digital interface, so we questioned our designers of how they think the digital interface ought to be. And again, we have the notions of it has to be informative, yet simple and easy to use. However, interestingly, they felt that the digital interface is not enough on its own as a form of interaction, and that there needs to be a more engaged approach. And finally, that the design should be, the design processes need to be centered on the principles of user-centered designs, need to be based on the principles of UCD. So how did the designers think of the users? The residential users, I put this in an exclamation mark because interestingly, lots of contradictory views that are held by the designer himself or herself has contradictory visions, and also the designers amongst themselves disagree with each other about the user. And this is not a bad thing, but something to highlight in the sense that the diversity of these opinions needs to be reflected upon, particularly when we think about adaptive DR frameworks. So the residential user was imagined as altruistic and community-orientated, environmentally minded, so cares about the environment, interested in sharing the energy from their renewable energy and doing their bit, and actively engaged and interacting with their neighbors and community. However, they were also economically motivated. So the idea is that people are very simple, they are financially driven and benefit driven, and that it all comes down to their economic benefit, and we cannot really have them on board unless it makes economic sense. So as you can see, there's a slight contradiction, and more so, the third representation of the user is this idea of a techno-abled or techno-educated user, that they are naturally inclined in their everyday life to engage with smart technologies and smart systems, and that they will make the right choices as soon as they learn how to engage properly. So this idea that they are educated, therefore they will make the right choice. They were also imagined to be young, because young people are more exposed to smart technologies and the concepts of electricity and the need to reduce carbon, etc. At the same time, they were also perceived as older generation because they care about their grandchildren's future and have the time, most of them would be retired and have the time to engage and finesse and align their consumption to the grid. So as you can see, these contradictory representations are very interesting. Clearly, there's a diversity of users that we need to take on board, and I will elaborate more later. And so also busy homemakers. So our designers were very much aware that the user is also someone who is busy, that they have everyday priorities and are time poor. And so there are many demands on their time, particularly parents of young children were perceived as not the indicated user of DR. So, So there was also acts of inclusion and exclusion going on in the thinking processes of the designers. Non-residential users, i.e. companies or offices, shops, etc., were understood to be constrained by the services that they provide. So, for example, they cannot postpone particular things that need to happen. A dishwasher needs to go on at different times in a restaurant's daily cycle, etc. Diversity in size and consumption. So you had the big companies that could provide a lot of flexibility due to their high load, versus smaller, local businesses. There's diversity of motivations. They could see that much like the residential user, the non-residential user was also imagined to be financially interested, but also willing to engage in social responsibility, to attract new customers, to have that kind of green branding. And finally, the employees of the company were, we tried to kind of talk about that. They were admittedly mostly absent from the mind of the designers, in the sense that they never really thought about how the comfort levels of the people working in offices that engaged in DR will fare. But to say that the idea is that it depends on the company, the age of the workforce, etc. And finally, the island communities were also, imagined as localities aligned with nature, exposed to natural elements, and can see the environmental damage to their communities after the tourist season is over. So, would be motivated to engage with renewable solutions. But at the same time, they are diverse with different energy needs and cultural traits, particularly in React, where we have 3 islands in very different national and geographic climatic context. They are close to each other and interact together a lot. That was the imagination. And I will form ideal experimental beds because of their awareness to the challenges of having their houses provided with electricity, and have the potential to be green because of their close networks. And however, also at the same time, particularly with smaller islands like Aran and La Graciosa, it doesn't quite offer the critical mass required for cooperative DR, so that was always something on their mind as well. So how does that compare to the reality of the users? As I said, we conducted a survey looking at the perceptions of the communities in these 3 islands. And this one, for example, states very different motivations that the users have. So the color in blue here is the strongly motivating, and the orange is motivating. And as you can see, they are strongly motivated and motivated by a variety of things, such as wanting to reduce their emissions and wanting to be high-tech at the same time, but also wanting to reduce their energy bill, particularly, for example, here in Carlo Forte, quite a lot of, almost 80% of the users were very much interested in reducing their bills. So as you can see, there's a variety of motivations. And I think one of the important things here is the alignment between the contradictory contradictory representations of the user versus the realities that the users themselves have a variety of reasons to want to engage with DR and the smart grids of the future. Similarly, the knowledge of and familiarity with the concept of smart grid, for example, is very low in the islands that we surveyed. Up to, for example, 60% in Carlo Forte do not have familiarity with the concept. And similarly, the never heard of it in blue here shows how a lot of the people we surveyed have not had any kind of familiarity with the different demand response technologies, such as smart battery or smart washing machine, of course, with the exception of photovoltaics and electric vehicles, because these are quite popular in the media, etc. So again, there is alignment, but importantly, it's important to indicate that there is a barrier, if you like, in terms of the knowledge base of the user. This is something designers ought to be aware of. So to conclude, the ambiguity about the way DR should be designed, the risk of manual DR leading to fatigue versus the difficulty of integrating demand response in people's busy lives. And data shows that familiarity and knowledge among users is low. So the designers who told me that the users ought to be educated are correct. However, there's always a but. Fixation with education and training users does not always translate into project designs that work. So in and of itself, the education is not enough. We have to think about adaptive demand response, the demand response that fits into people's everyday life, as Michael has just talked about, in order not to exclude, for example, parents with young children, and to think about DR more holistically. It is imperative, we argue, to let go of the techno-abled notion of the user. So this idea of the clever, inclined user who will just get on with it, because this is a barrier in action and in also the research of DR. There are tensions across different user motivations, contradictory notions, as I have indicated, idealized users versus the real users, as the statistics have shown. So, what does that mean? You will say to me, okay, Dana, we now know, you have told us how we think, we know how we think. What do you want us to do? Well, one thing to consider is the co-production approach, a broad umbrella of thinking when it comes to demand response design and implementation, that will bring together efforts such as adaptive DR frameworks, co-design of digital interfaces. So it will bring all these kind of notions together. So thinking more broadly about co-production, where the service providers and users work together to reach a collective outcome. So here, because at the end of the day, the prospective DR users are the best placed people to design it. And we have to work with them, to co-design with them, to co-produce with them the implementation projects, and enlist useful concepts such as user-centered design. So in order to do all that, we have to think more broadly in our approach. Move away from the notions of the, my colleague, Professor Crosbie would like to call naughty users, who ought to change their behavior, this sort of moralizing, disciplining notion of what the DR is here to do, and instead to transform the nature of interventions to center the user, because at the end of the day, all the designers that I spoke with agreed that the user is at the center of it. So let's put that into action. Let's try and make that into a workable solution in our approach in the future. So yeah, centering the user as the expert in understanding how the art can fit into their lives and businesses. And I think this pretty much, these are some of the references if you are interested in my weird background in sociology. And thank you very much for listening. If you have any questions, do we have time for questions?
Yes, we can use
maybe 1 minute.
5 minutes.
Yeah. To the lunch.
Yeah, but maybe like 1 minute for questions. Sorry about that. I try to be as quick as I can. Thank you for listening.
One quick question. One thought I've kind of had, what might make sense, given all of the issues around DR and changeability, somebody working from home 3 days a week, and when they're in the house, really keen, will run around switching cameras off, doing this, that, and the other. But then they get another job, and they're only working from home 1 day a week. So we have to kind of adapt to that. And what would things like looking at a lower price energy tariff, if you show that you can and can do, can participate in the best way that you can, you can kind of make a lower price tariff available as an option for an energy company. Are those the kind of solutions that we might need to start thinking about?
Perhaps, yeah. I mean, yeah, perhaps. I mean, I'm not married to any particular solution. I think there's a variety of solutions, and this is where it comes to the multidisciplinary nature of the teams who ought to be co-producing alongside the users, the variety of solutions that could be possible. So yeah, absolutely.
You have like a notion of the community tariff.
Perhaps, yeah.
Green, amber, red. so everyone gets a bit of feedback as the community going to be on this lower tariff next year.
Yeah.
Or are we looking at paying more?
Exactly. Yeah. So
more could I do?
Yeah.
Doing enough.
Almost having like
having the thing appointed, like you already know the use it.
Yeah, exactly. Yeah, almost having like a collective bargaining approach to what that means regarding the financial aspects of it, because the data has shown that people are obviously also care about their economic benefits. So yeah, absolutely. And it's really interesting that you raised the point about changing their circumstances. You know, they would be working from home and then they get another job. Because some researchers in my field, some social scientists have actually looked at, they call them energy biographies, you know, people who before they retire and after they retire, or they retire and then they decide to volunteer at a community. Obviously, then in that case, they have to, you know, take the bus, and so their behavior changes. Even though they are retired, they are leaving the house for long periods of time to, for example, volunteer, etc. So yeah, having the kind of approach of like perhaps DR contracts that are adaptable to people's changing circumstances, and yeah, it's trying to imagine with the user what they are like and what could be flexible for them. And yeah, and I mean, it's interesting because on the one hand, it's very difficult to explain demand response to an average person. On the other hand, our fixation with the concept of flexibility for us here in this room means something completely different to when you say to the user flexibility. To them, you are the one who are supposed to be flexible to their needs, versus we are thinking they ought to give us flexibility. So it's bringing those you know, opposing views together in a co-productive approach.
Trying to find something that works in a competitive market as well, even if it's regulated.
Yeah.
The reality of the situation.
Quick from my side, I may have missed it in your presentation when you talked about this. What about, have you interviewed residential users also about their willingness or acceptance with regard to changing the schedule of heating systems? Because we're going in that direction that we have more and more heat pumps, so electric heating. And of course, this is also a way, but then many, I know from the practice in my country that many users in the past, in district heating especially, they tried the companies to reduce temperatures in some hours and maybe increase in other hours. But then if you reduce the temperatures of your radiators during the day, then people won't feel it. So although maybe the inside temperature is okay,
yeah,
but they have this habits,
yeah,
to feel the radiators hot. So have you also investigated on this?
So for the React, not yet. We have survey data that I will present. Actually, what are you doing in the early afternoon session? Come to my paper. I will be talking more in detail about the survey that we conducted. So we did actually ask about the willingness. However, the next step for us in React, which will happen in the next few months, is to conduct qualitative interviews to find out about those exact preferences that you point out. Because, I mean, from my experience from previous projects, people wanted to go over the radiator to check if it's going, even regardless, as you say, whether they are comfortable or not. So, so you are right. This is an issue. People have shown a preference. I can't remember how prevalent that was, but this idea of checking that it's working is there. So yeah, and perhaps I can elaborate more on the side about this because it was from a different project a long time ago. But yeah, absolutely spot on about that.
Flexibility
in heating, yeah.
I never quantified it, but I believe it's pretty high.
It is, yeah, and obviously we have like the direct load control, automated ways of doing it, and then other ways. And so, which approach is best, and how sensorial is heating and cooling the house, and all that is interesting, yeah. Any
Other
questions
questions?
online?
Online, we no questions. So.
Thank you, Marco, and thank you all for being here.
So thank you very much for the people connected in a remote mode. And sorry if we collected some delay. If people online want to ask something, you can directly put your question in the chat, and then I can send you by mail, or I can connect you directly with the person indicated. So thank you very much, and see you soon in the next Sustainable Places.